Yes. Good morning, one and all.
Good morning, sir.
Morning.
Morning, sir.
Yeah.
Good morning, sir.
Good morning, sir.
Okay. So I welcome to this session. So yesterday we have discussed about this downlink transport channel processing, the first part. As I said, in the downlink transport channel processing, there are two steps. One is the channel coding process, and second one is the modulation process. So yesterday we have discussed about the channel coding process. Okay. Sorry. So this is a channel coding process involves the adding of cyclic redundancy check bits to the transport block. See, the transport block is the data or control information coming from the MAC layer, right? So for that, as a first step, the cyclic redundancy check bits are added. Okay, the purpose of adding CRC bits to the transport block is for error detection. And what would be the length of the transport block? See, the length of the transport block in LTE is taken as one subframe duration. Okay, see, one subframe duration in LTE, which is equal to 1 millisecond. Okay, so that is the length of the transport block. And as I said, CRC, which is of 24 bits, are added. That is the first step. Then after adding, that will be compared with the maximum code size. Okay, if the transport block plus CRC bits is less than the maximum code block size, then it will be retained as it is. Otherwise, the code segmentation will be done. Means if the transport block plus CRC bits is greater than the maximum code block size, as I said, which is 6144 for turbo coding, right? So that will be segmented. Okay, based on what? Based on the formula what I said, C is equal to B divided by Z minus L, where B is transport block plus CRC divided by Z is maximum code block size and L is the CRC bits. Okay, so after segmentation, what is done? Then coding is done, and that is channel coding is done, right? So in channel coding, we use two types. One is tail bit convolutional coding with a coding rate of 1/3, and another one is turbo coding. I said again, there are two methods to terminate the release, right? So one is padding, by padding zeros at the end of the code block, and another one is tail byte, right? So I said the tail byte is the most efficient one compared to other method. After channel coding, the next step is the rate matching, right? So Rate matching involves refitting the size of the transport block to fit to the payload. Okay, then that involves, that rate matching involves cell selection and cell level. Okay, after that the concatenation will be done. Okay, code concatenation. So till that I thought, so that is about the channel coding process. So next is modulation process. So which take full screen. Yeah. So this modulation processing involves, means the input to this modulation process is output of that channel coding process, right? So that is the code words, which will be, means this modulation process has 5 stages. One is scrambling, then modulation mapper, then this layer mapping and pre-coding together is known as the MIMO signal processing operation, then the resource element mapping, then the OFDM signal generation. Okay, so the output of channel coding process is the code word. Okay, that will be applied to the scrambler. So this scrambler will do the scrambling. So do you have any idea about scrambling? What type of code is used to do the scrambling and all? So this scrambling is done by using pseudo noise code. Okay, so which is of 31 bit length. As I said, it is a code sequence. Okay, so output of that scrambler will be applied to the modulation mapper, I said. So here in modulation mapping means that bits, okay, whatever we are getting from the output of the scrambling will be mapped to in phase and quarter share components, that is IQ. Yeah, this is what about scrambling. Yeah, so I was telling in scrambling, the code word is the input to the scrambler, right? That code word will be what? Output of the channel coding process that will be first scrambled by bit level scrambling sequence. So that will be denoted as like this. See, the block of bits for code word, the block of bits for code word Q is denoted as this one, BQ of 0 to BQ of MB to the power of Q minus 1. So this is the block of bits for code word Q. Okay, so where MB to the power of Q is the number of bits transmitted in one subframe. I said here the transport block will be equal to one subframe length, right? And the scrambling sequence, which is denoted as C to the power of Q, is a pseudo random sequence, I said, right? It is a pseudo random sequence. So it is a pseudo random sequence, and which is defined by what? 31 length gold sequence. I think this we have discussed in DC class, right? In spread spectrum communication, I said how 231 bit length will be XORed, and we are getting the gold sequence. So that is the scrambling sequence, and this scrambled bits are generated using, I have written here, modulo 2 addition, right? So which is denoted as B. I think this is B to the power of Q. No? I think it will be denoted like this with symbol. Okay, so everywhere it is with this B negation Q of I is equal to this one, B Q of I plus C Q of I modulo 2 operation. Okay. As I said, this is the scrambled sequence, which is generated by using 231 bit length gold sequence, right? Which is XORed by using modulo 2 operation. Okay. Come out of this full screen, I think it is stuck. Okay. You can hold not control what is not control. Yeah, as I was telling, this scrambling is done by using pseudo sequence, which is of length 31 bit, the gold sequence. Two 31 bit M sequences are XORed to get the scrambling sequence. So here we can use up to two code words. Okay, two code words can be transmitted in the same subframe. Yeah. Okay, so up to two code words can be transmitted in the same subframe. And I said Q is the code word, right? So that will be equal to 0 if the spatial multiplexing is not used, and means, and if I use the spatial multiplexing, the Q is, that is the code word, will be two code words. So scrambling sequences are different for neighboring cells. So why we do have different scrambling sequences for the neighbor cells is to limit the, or to mitigate the intercell interference. Okay, so that is what it is written here. Intercell interference is randomized so that the intercell interference can be mitigated by having different scrambling sequences in the neighbor cells. Okay, all the downlink transport channels and control information will be done like this. Scrambling sequence for different are different for neighboring cells, except the multicast channel. Okay, so for multicast channel, the common scrambling is applied, okay, for all cells. Okay, So usually the multicast channel is used for this MB-SFN transmission. So I said MB-SFN is a multicast broadcast single frequency network. So only except multicast channel. So rest all the downlink transport channel and control information is done the scrambling sequence, which is different for the neighboring cells. Okay, that is about the scrambler. Okay, the output of channel coding is a code word which will be passed through the scrambling scrambler. Then output of scrambler is applied to the modulation mapping. So here for each code word Q, the block of scrambled bits, the scrambled bits are denoted by, this is B negation of Q of 0, okay, to BQ of MB of Q minus 1, okay. These are the, these code word output of the scrambler are modulated into the block of complex valued modulation symbols. Okay, the complex valued modulation symbols are denoted as dq of 0 to dq of ms to the power of q of minus 1. So this m suffix s to the power of q minus q is nothing but the number of modulation symbols in each code word. Okay, see, code word is the input of scrambler. Output of that sequence scrambler is denoted like this. This is the output of the scrambled block. Okay, that will be mapped to certain modulation symbols. So this ms to the power of q is a number of modulation symbols in each code word, and that depends on the modulation scheme. So if I use a modulation of QPSK, then the symbols will be 2, right? If I use 16 QAM, then the modulation symbols will be how many? Means if I use QPSK, I said it is 2 modulation symbols or 4 modulation symbols. It is 2 bits is 1 symbol, so I get 4 symbols, okay, for QPSK modulation, and for 16 QAM, I get 16 symbols, right? That is with 4 zeros to 4 ones. So like so that this depends on ms to the power of q is about modulations. Number of modulation symbols, that depends on type of modulation scheme I use. Okay, what is the relationship between this the modulation symbol and the block of scrambled code word? Okay, so the modulation symbol, which is equal to scrambled code word divided by the number of bits in the modulation constellation, that is q suffix m. Okay, mb to the power q by qm. So here the value of qm depends on what type of modulation I use. If I use QPSK, so number of bits in the modulation constellation is 2 for QPSK. For 16 QAM it is 4. For 64 QAM it is 6, and so on. Okay. So ms to the power of q is the what? Number of modulation symbols in each code word. Okay. mb to the power of q is the scrambled code words. So that is what is written here, right? Means what are the different types of modulation supported in LTE? Or it supports QPSK, 16 QAM and 64 QAM, and BPSK also. Okay, this BPSK is used only for this channel, that is a PHICCH channel. Okay, that is a physical hybrid ARQ indication control channel. PHICCH means this is a physical channel. So here just I have written what is the physical channel and what type of modulation is used for that particular channel. Okay, so that is a physical downlink shared channel, supports means uses QPSK, 16 QAM and 64 QAM, and this is physical multicast channel. Okay, this uses QPSK, 16 QAM and 64 QAM, and physical broadcast channel uses QPSK. This is PCFICH is the physical control format indicator channel. PCFICH is the physical control format indicator channel that uses QPSK. And next one is PDCCH, that is physical downlink control channel, also uses QPSK modulation. And only PHICH uses BPSK modulation. So PHICH is the what? Is the physical hybrid ARQ indicator channel. So that is about modulation process. So we have understood what is the relationship between, means how code words are scrambled, that scrambled sequence, how it is mapped to the modulation symbols, right? And what type of modulation supported for each transport channel. So next step is the layer mapping and pre-coding. Okay, these two blocks together is known as MIMO. There is multiple input, multiple output antenna processing stage it is. Okay, so for this means output of the modulation mapper is applied to the layer mapping. Okay, so what actually this layer mapping will do is it will map the code word to the V number of spatial layers. Okay, see, input to the layer mapping is the code word which is from the modulation process, right? Which is from the modulation mapper, right? So as I said, in modulation mapper only two code words are used. Means there is code word 1 and 2, right? So only one code word will be there for spatial multiplexing is not used. There will be two code words if spatial multiplexing is used. Right? So that is the input of the layer mapping. So layer mapper map the code word correspond to the V spatial layers. So how this NC and V are related? Let us see this. Means as I said, the maximum value of NC, that is code word, is only 2. Okay, the V layer can vary. That depends on it may be 1, 2, 3, and so on. Okay, and the output of this layer mapping, okay, will be applied to the precoder. So the precoder maps the V layers to P antenna ports. See, output of the precoder is mapped to the antenna ports. So here there are different antenna ports, like antenna port 0, 1, 2, 3, and so on. And it is categorized into 3 different types. I will come to that. So the thing is here, code word will be mapped to V layers, and V layers are mapped to P antenna ports. So together, as I said, these two blocks will be the MIMO related signal processing operation. So as I said, the code word is the output of each channel coding or rate matching stage, right, associated with the single transport block coming from the MAC layer. Just what code word is. Right? So as I said, in LTE, the number of code words are limited to 2. So why the number of code words are limited to 2 is here to limit the uplink feedback overhead. Okay. So that is why the number of code words limited in LTE is only 2. Because as we increase the number of code words, the uplink feedback overhead will increase, because the user equipment has to give a feedback about the quality of channel to the ENB. So that is done by using this process, that is a hybrid ARQ process, right? So a separate hybrid ARQ process is used for each code word. So that requires separate signaling in the uplink control channel. So if I use more number of code words, obviously I need to use more number of HARQ, that control signals, that will be increasing the overhead, feedback overhead, right? So to overcome the problem, the number of code words are limited to only 2. So this is about code word, right? Similarly, layer mapping, I said, no, that layer corresponds to the data stream of the spatial multiplexing channel. So I hope you are aware of what is spatial multiplexing. That is, spatial multiplexing is nothing but MIMO only. Okay. So a layer corresponds to the data stream of the spatial multiplexing channel is the layer. So each code word is mapped into one or multiple layers, right? So that depends on what type of MIMO mode is used. Okay. Uh, okay. So here the number of layers, that is spatial layers, will be always greater than or equal to the number of code words. Anyhow, the number of code words are limited to only 2. Okay. So I said I was talking about antenna port now. So means output of the precoder is mapped to antenna port. I said. So antenna port is defined as, so it is associated with the type of reference signal. So there are different types of reference signals in LTE. I will come to that even in uplink and as well as downlink. So as I said, this antenna port is defined by its associated reference signal. Okay. Means to what reference signal it is associated, accordingly we define the antenna port. And it is basically a logical entity, and it may not be corresponding to the actual physical antenna. Okay, that is the antenna port. As I said, antenna port will be associated with the reference signal. As I said, it is a logical entity and it may not correspond to the physical antenna. Okay. So the number of transmit antenna ports at the ENB is sent to the user equipments through this channel, PBCH, that is a physical broadcast channel. Okay. So these antenna ports may be 1, 2, or 4 in LTE. Okay. So the antenna ports are divided into 3 groups. Antenna ports 0 to 3. Okay, that is antenna port 0, 1, 2, and 3. So these 4 ports, right, from 0 to 3 are cell specific. So which are used for downlink MIMO transmissions. And next one is antenna port 4, that is MBSFN specific. Okay, the MBSFN, what I said, it is a multicast broadcast single frequency network. Okay, so antenna port 4 is MBSFN specific and is used for MBSFN transmission. And antenna port 5 is user equipment specific. So these are the 3 different categories: cell specific, MBSFN specific, and user equipment specific. Okay, so antenna port 5 is user equipment specific and which is used for beam forming to a single user equipment using all physical antennas. Okay, just to show about that idea about antenna ports, right? I said cell specific ports and the user equipment specific port. So cell specific ports and user specific ports cannot be simultaneously used. That is one limitation here. And what I said, antenna ports 0 to 3, right? Antenna port 0, 1, 2, and 3 are used for cell specific. Okay, they're all used by the downlink transmission. Fine. So here port 0 means this is for single antenna transmission, and port 0 and port 1 is used for 2 antenna, that is transmit diversity and spatial multiplexing, and from port 0 to port 3. Okay, this is used for 4 antenna transmit diversity and spatial multiplexing. In the last slide, I said about this. See, the number of transmit antenna ports at the ENB, right, is sent to the user equipment through PBCS channel, which can be 1, 2, or 4. That is what the meaning here is: 1, 2, or 4. So 1 is single antenna, 2 is 2 antenna, that is a transmit diversity and spatial multiplexing, and 4 is, that is from port 0 to port 3, that is for 4 antenna. See, in LTE, it supports maximum 4x4 MIMO. And actually port 5, right, I said it is used for beam forming. Port 5 is used for beam forming. Okay, so I was talking about that layer mapping and the precoder, right? So for V layer transmission, means I said the number of layers, that depends on the type of MIMO mode operation, right? So for V layer transmission, the modulation symbols can be denoted as this: dq to the power of 0 and so on up to dq to the power into ms to the power of q minus 1. Okay, so for code word q, that will be mapped onto the layers. That's how we map that code word modulation symbols into this V layers. Okay, so the output of the V layer symbol will be denoted like this: x of I will be equal to x0 of I and so on up to xv minus 1 of I transpose it is. Okay, this is a transpose matrix, and this ms to the power of layer is the what number of modulation symbols per layer. Okay, ms the power of layer is the what I said number of modulation symbols per layer. So this layer mapping is different for different MIMO modes, I said. That means if I using only single antenna port, then there will be one code word is mapped onto the single layer. Okay, if I use transmit diversity, means I'm going for 2 by 2. See, one code word is mapped to 2 or 4 layers. So one code word will be mapped to 2 or 4 layers in case of transmit diversity, whereas we are using 2 by 2 antennas. So in case of spatial multiplexing, see the number of code words are mapped to V layers. So the number of code words in case of spatial multiplexing, I said it is 2, and the number of V layers will be 4. 1, 2, 3, 4. So as I said, always the number of V layers is greater than the number of code words. So this is what about V layer, that is layer mapping. And here I have written what type, which code word is used, means the number of layers. Okay, code word to layer mapping for spatial multiplexing. See, yeah, yes, two code words. No? One is code word 0, another one is code word 1. See, means if I use a single antenna, only one code word will be there. So one layer. So the number of layers will be 1. Okay, means if I am using 2 by 2 antenna, right? That is transmit diversity, and here there will be 2 code words. Okay, 2 code words. That is code word 0, code word 1. I can map code word 0 to layer 0 and code word 1 to layer 1. So 2 layers. The number of layers will be 2. And I can have only one code word can be mapped to 2 layers. So that is layer 0 and layer 1. So this will be done at the beginning only. Okay. So during that time also the number of layers are 2. And the next one is I can map code word 0 to layer 0 and code word 1 to layer 1 and 2. So here the number of layers will be 3. So next possibility is I can map code word 0 to layer 0 and 1 and code word 1 to layer 2 and 3. Okay. Here the number of layers will be 4. Okay. So output of layer mapping, so that depends on whether I use in a MIMO mode, that is single antenna or 2 by 2 antenna or 4 by 4 antenna mode, right? So depending upon that, it will map that code word to different layers. So I said the precoder takes the block of vectors, means output of V layer mapping unit as xi as input and generates the block of vectors, means output of the precoder will be written as y of I, which is equal to y naught of I and so on up to yp minus 1 of I. This is also transpose matrix. Okay. So here as ms to the power of ap, that indicates, so output of precoder map to one resources on each of the antenna ports. See, output of the precoder is given to the resource mapper. So next block is that, right? So output of the precoder will be mapped to one resources on each of the antenna port. So yp of I is the signal for antenna port P, and ms to the power of ap is the number of symbols on each antenna port. Number of symbols on each antenna port. So the precoder, maybe it is fixed or selected from the predefined code book. Okay, so based on the feedback from the user equipments. So in general, what we can write for pre-coding is, so output of the pre-coder is y of I said, right? So which is equal to wi into x of I, where wi is the pre-coding matrix, and the size of the pre-coding matrix is p into v. So p is the number of antenna ports and v is the number of v layers. That is the size of the pre-coding matrix. And this table tells you which channel supports which mode. Okay, supported MIMO modes for different physical channels. So physical channel, physical downlink shared channel supports all three types. Single antenna port. That is OL means open loop transmit diversity. So in transmit diversity, we have open loop and as well as closed loop. I will discuss about that later because I have not taken that part, MIMO part here. Okay, so physical downlink sharing channel supports all the three types: single antenna port, open loop transmit diversity, and spatial multiplexing. Then this physical downlink control channel supports single antenna port and OL transmit diversity. Okay, so here only this PMCH, that is what physical multicast channel, is only for single antenna port. Okay, so rest all will be supporting at least minimum 2, right? That is this one, physical control format indicator channel support single antenna port and as well as open loop transmit diversity, and this also physical hybrid ARQ indicator channel support single and as well as open loop transmit diversity, and this physical broadcast channel supports single antenna port and OL transmit diversity. Only the physical downlink shared channel supports all three modes of the MIMO. Okay. So resource mapping is the next block, right? That is output of precoder goes to resource mapping. See here, in case of resource mapping, each of the antenna ports, right, used for transmission of physical channels, right? So the block of complex value symbols, the output of that will be written as what? YP of 0 and so on up to YP of ms to the power of AP minus 1, right? Means this is the output of the precoder. That will be mapped in sequence starting with YP of 0 to resource blocks assigned for transmission. So the moment I say resource block, you should visualize that bathroom tailbox structure, right? That is y-axis 12 subcarriers and x-axis for one time slot, that is 7 OFDM symbols, or 2 time slots, that is 14 OFDM symbols. So in that I written resource element, right? One small box is the resource element, and that is, this is y k and L is of x axis, right? So that will be mapped to that antenna port. So the mapping to resource element k comma L on antenna port P, so not reserved for other purposes, will be increasing in order of the index k and then the index L. Okay, starting with the first slot in the subframe. So first slot, from there it starts assigning the or mapping to the resource element of the output of the precoder, that is antenna port. Okay, I think the next stage is the means output of this resource mapping is applied to the OFDM, that is